Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. We are now discussing about the second unit of this course, the Molecular Luminescence Spectroscopy. It is the first lecture of the sixth week. Myself, Dr. Mohammad Zain Khan, working as Assistant Professor in the Department of Industrial Chemistry, Aligarh Muslim University, Aligarh. In the last class, I have explained you about the instrumentation of fluorescence spectroscopy. We have discussed about the various components of spectrophotometers. Those components include the light source, the monochromators, the photodetector. Actually, there are two monochromators used, one before the sample tube, then we have one more, and then we have one more monochromator after the sample tube, and finally we have a photodetector followed by an amplifier and output device. Out of these few components, we have completed the light source, and there are three types of light sources. The mercury lamp, but because of their lower intensity, they are not much prevalent these days. Then we have xenon lamps, which are further divided into two categories: xenon arc lamp that provides a continuous bright light, while xenon flash lamp that provides a very high intensity bright light, but for a very short period. In addition, I have also explained you the flow sheet of a spectrophotometer, how light source creates the light radiation, and those light radiation passes through the monochromators into the sample tube, then again pass to the second monochromator. The second one is called as emission monochromator, while the first monochromator is called as the excitation monochromator, and finally the light falls on the photodetector, followed by our amplifier and the output device. Let us discuss the second important component of a spectrophotometer in today's lecture, and that component is the monochromator. As you all know, because we have already discussed about monochromator in the previous unit as well, that where we were focusing on the atomic absorption spectroscopy and atomic emission spectroscopy. Monochromators are the devices which are used to filter the light radiation. They disperse light radiation, a single light radiation of which consists of a long region of electromagnetic spectrum, into its individual light radiation, and then we can allow some of these light radiation to pass through it, while rest of these radiation can be blocked. And therefore this monochromator consists of two basic units. First is the prism, or we can use a molecular grating, which has the capability to disperse or distribute light radiation into its individual narrow wavelengths. And then we have two slits. One is the entrance slit, the other is the exit slit. The exit slit helps us to select a particular wavelength of light while excluding the others. So monochromators basically act as a light filter from mixed source, sending light radiation of mixed wavelength. We can convert light of specific wavelengths. And since this fluorescence spectroscopy involves two types of signals, it has an excitation signal, then it has an emission signal, which means that there are two wavelengths of light. In the first case, the light radiation of the incident radiation is passed through a monochromator, then it enters into the sample tube where it is being absorbed by the sample, and electrons are excited to the higher level. When those electrons returns back, they create light emissions. So in the second case, the wavelength at which light emission are taking place, it is called as the emission wavelength, while in the first case, when absorption of light is taking place causing excitation, it is called as excitation wavelengths. So we have two monochromators, and both these monochromators consist of two slits. One is the entrance slit, other is the exit slit, and in between we have a grating or a prism. So we use a combination of entrance and exit slits along with the grating or a prism. So a monochromator directs light through the entrance slit and then disperses this light radiation into individual narrow wavelength light radiation with the help of a grating or a prism, and then it further focuses those light radiation towards the exit slit, which select few light radiations while blocks the other. In this way it acts as a filter, and those radiations that are allowed through the exit slit, they finally entered into the sample tube, causes excitation. Similarly, after interaction with the sample causing excitation, and then we have some emission in the form of fluorescence light, visible light. These emitted light radiations again enter into the detector, and I hope you all remember that detector in case of fluorescence is placed at 90 degree because we do not want to detect the signal from transmitted light. Therefore, we always place the detector at 90 degree, while in case of UV visible spectroscopy, the detector is placed in front of the sample tube so that it collects all the transmitted light radiation. Clear? So we have so the light so the emitted light again passes through a monochromator which select few light radiation through exit slit, and some of and only those light radiations falls on the photomultiplier tube, causing the signal to causing the spectrum to form on the output device. Differential grating is quite preferred for this purpose. This is a schematic diagram of a monochromator. It consists it consists of an entrance slit. The light coming from the light source enters the light coming from the light source entrance through these entrance slit, and these light radiations of broad wavelength, they falls on the concave mirror which acts as a collimating mirror. To collimate the light, it is being reflected to the grating. A differential grating is used which disperses this light into individual color. You can see here we have these white lines. This shows that the white light of broad wavelength range is coming into the monochromator, and when it falls on the differential grating, it is being reflected by this differential grating and dispersed into individual colors. You can see here the different color light radiations that are being formed when the ordinary light is diffracted, when the ordinary light is being distributed by the differential grating. These light radiations again falls on a concave mirror. This time the purpose is to focus the light radiation, so it acts as a focusing mirror. This one is the focusing mirror, while this one is a collimating mirror. After falling on the focusing mirror, in this graph only the functioning of a single monochromator is shown, and therefore a photomultiplier tube is placed. But in case of a spectrophotometer, we have when these focusing light and when these focusing mirrors they are reflecting the light radiation, we have an exit slit, and after passing through these exit slit we have a sample tube. And after when the flow and when excitation as well as emission occurs resulting into the fluorescence light, then we again have a monochromator which is having an entrance slit to allow these light radiation. Then there are mirrors used, collimating mirrors that transfer light to the grating. Then we have a grating, then collimating mirror which transfers light on the grating, and then these light radiations converted into individual colors. Then we have a focusing mirror that then transfer those light radiation through exit slit, and finally we have a photomultiplier tube as a detector, or a charge coupled device based solid state array detector. Finally, the spectrum is obtained on a display device. Which is computer. Then comes the detector. Light after passing through the monochromator, or I should say more correctly the emission monochromator, the light falls on the photomultiplier tube which is used as a detector. And if photomultiplier tube is not used, or in case of a multiple element analysis, we used solid state array detectors, which I am going to discuss later. First we discuss the photomultiplier tubes here. And as you all know that photomultiplier tube, it is a photo responsive equipment. It is photosensitive, where we have a quartz window which allow the light radiation coming from the sample, the emitted light radiation, which is a fluorescent light, enters through this optical window, and then we have a photocathode placed over here. So this is our photocathode. When the light radiation, when the light photons are absorbed by this photosensitive cathode, electrons are emitted. So photons are coming, they fall, electrons are emitted. and since the intensity of emitted light is low, a small amount, so as you are, so this is our photo sensitive cathode that is placed over here. When the light ray photon falls on it, electrons are ejected, and as we all know that the intensity of light emitted is quite low, so the number of photons reaching this photoanode are also low, creating or ejecting lesser number of electrons through the effect, creating or generating lesser number of electrons through the phenomena of photoelectric effect. Photoelectric effect. Now these electrons then falls on dinodes. There are few more metallic dinodes placed. When these electrons known as primary electrons, these are known as primary electrons, they falls on these dinodes, again there will be ejection of electrons from the dinodes. They are called as secondary electrons. Now when these photoelectrons falls on the first dynode, more number of secondary electrons are ejected. Then these secondary electrons falls on the second dynode, then even more number of secondary electrons are ejected, and in this way there are few dinodes placed on the path, so that these electrons falls on those dinodes, resulting into large number of accelerated electrons, and these accelerated electrons then falls on a anode, creating electrical signal, creating current. And in this way an electrical signal is generated, and depending upon the intensity of light that is being emitted by the sample, there will be more. If the intensity is more, the number of primary electrons ejected will be more, and since the number of primary electrons ejected is more, they ultimately creates more secondary electrons from the diodes, and finally the electrical signal would be high. So while working on these photomultiplier tubes, we should keep it in mind that the thickness of this photocathode is very important, because the thickness of this photocathode basically controls the quantum efficiency. The quantum efficiency of the photomultiplier tube depends upon the thickness of the photocathode, and in general the photomultiplier tubes that are used, they have a quantum efficiency ranging from 30 to 70%. Some of them have very low quantum efficiency of 30% only, while some good quality PMT or more sensitive photomultiplier tubes have quantum efficiency of up to 70%. Now this quantum efficiency depends upon the thickness of the photocathode. If the thickness of the photocathode is very high, then in that case, if the thickness is high, more number of photons will be absorbed while very little electrons are emitted. More photons will be absorbed and low number of electrons, and less number of electrons are emitted. On the other hand, if the thickness of this photocathode is very fine, it is very thin, then most of the photons go unabsorbed. So this means that the thickness should be in between. Thickness should be moderate. We have to maintain it such that the thickness should be moderate and quantum efficiency should be high, because if the thickness is high, if the thickness of this photocathode is high, electrons will not be ejected even after absorption of large number of photons, which means that after absorption of large number of photons, only very few electrons are being emitted. On the other hand, if the thickness is very small, if it is very thin photoconductive for material used for making this photocathode, then when many of the photons goes unabsorbed, and when they are not absorbed, no electrons will be ejected from the photocathode. Clear? There is another important term used in case of photomultiplier tube called as photoconductive gain that I have already explained you, which means that the enhancement in the current signal upon absorption of light photons, or the enhancement in current signal for or enhancement in the electrical signal upon absorption of one single photon of light. So this is a schematic diagram of a photomultiplier tube where we have an optical window through which the light radiation, incident light radiation, through which an emitted light radiation is coming, which falls on this photocathode placed over here. Then after passing through the photocathode, the electrons are ejected. These electrons are then focused on different dinodes. These are the primary electrons that are ejected. They falls on the first dinode, creating more secondary electrons. Then these secondary electrons again falls on the second dinode, creating even more number of accelerated electrons, and in this way these new electrons falls on the next dinode, creating even higher number of electrons with high speed, and finally these electrons reaches to the cathode, so that a measurable signal is obtained, and that signal is further amplified by using an amplifying device, so that a readable and useful signal is obtained and a reliable spectrum is generated. On the other hand, we also have solid state array detectors that are also mentioned here. We have some machines that are called as solid state detectors that basically works on either charge injection device or charge coupled device. So we mostly use charge coupled device based detectors. They are made of semiconducting materials, and the beauty of semiconducting materials is that their conductivity is in between insulators and conductors. Insulators have valence and conduction band overlapping with each other, so the electron can easily move from valence band to conduction band, while in case of insulators there is a large gap, so that electrons cannot go from valence band to conduction band. But in case of semiconductors, this difference of energy, or the band gap, is in between these conductors and insulators, and this difference can be further reduced by either doing some sort of doping or by increasing the temperature of these materials. So there are a number of ways, and one more way to reduce the gap of these valence and conduction band of semiconductors, so that electrons can easily jump from valence band to conduction band, thereby conducting electricity, is to irradiate these semiconducting materials, which means that just incident some light radiation upon it, which has sufficient energy so that electrons are promoted, and then they can easily reaches to the conduction band. When the electron reaches to the conduction band, when the electrons are reaches to the conduction band, a vacancy is created in the valence band, which is represented as hole, while the electrons are represented in the conduction band. These charge carriers, electron and hole pairs, they basically creates an electrical signal in these devices, and these devices are even useful for the detection of multiple elements at a time. They are capable of detecting multiple elements at a time, because these solid state array detectors, they have a plate on which there are different light sensitive materials arranged in an array, and these light sensitive material, each square is able to detect one material. So in this particular plate we have numerous squares, we have multiple squares present, which means that multiple light sensitive elements are there, which can capture the photons coming from different sources, which can capture the photons coming from different elements, and those elements can be detected simultaneously. So the beauty of these solid state array devices, because that they consist of light sensitive material called as charge, and they are coupled to capacitors. Once the photons falls, they create electron and hole pair, and these charge carriers, they create an electrical signal. So they also detect, just like photomultiplier tube, they also capture the light radiation, they also capture the light photons, which results into the formation of electron hole pair, which then captured by the electrodes, and finally an electrical signal is obtained. So in this case also we have an ultra thin window. It is an optical window through which light can pass, just as in case of 40 multiply tube we have an optical window. So the light radiation that is coming from the sample as a fluorescence light radiation, it passes through this optical window and it falls on the it falls on a semiconducting device. This is a silicon based semiconducting material. When it falls, it creates an electron and hole pair. Those electrons travel to the other side, creating an electric signal, and this portion is filled with vacuum, so that there is no possibility of these electrons to be captured by some other molecule. For example, if we have air or oxygen present in this particular space, the electrons, as soon as they are formed, the electrons, as soon as they are released, they are immediately taken up by oxygen, because oxygen is a very good electron acceptor. So oxygen will accept those electron forming radical, and then those electrons could never be reached to the other side of the system, could never be reached to the electrodes, and in this, and no current signal will be obtained. So since I have already covered these two, this is again about photomultiplier tube that I have already covered. Just in a nutshell, it has photocathode and normal anode. Fluorescence emission light radiation falls on photocathode, releases electrons. These electrons are accelerated and multiplied with the help of diodes. These are the diodes, and finally they are collected on the anode. Electrical signal is obtained. These photomultiplier tubes are used in UV visible, even in near IR ranges, and they are also used in AES, and molecular fluorescence spectroscopy. They are specifically used in UV visible region as well as in IR region, and all these techniques, atomic absorption, atomic emission, and molecular fluorescence spectroscopy, they generally operate in these regions only. So therefore PMTs are used in all these techniques. Again, we have a solid state array detector. Just in a nutshell, they use semiconducting materials. When light falls or they absorb light radiation, they create electron hole pair. They are called as charge carriers. An electric field is generated, and these electron hole pair moves towards the respective electrodes, producing a current signal. The current generated is proportional to the amount of light, because amount of light basically controls the number of electron hole pair. Intensity of light falling on the semiconducting crystal is more, of course there will be more number of electrons and hole pairs, and ultimately the current response would be high. Further, the solid state detector must be completely vacuum. They should not be air or oxygen gas, because oxygen can accept electrons as an electron acceptor, ultimately reducing the electrical signal. Silicon and germanium are used as a semiconducting materials in these type of detectors. As I said earlier, these semiconducting materials can be doped with other material so that their conduction and valence band comes closer to each other, and electrons can very easily jump from valence to conduction band. If we are not doing doping, we can either increase the temperature, or we either provide light radiations, because even light photons have sufficient energy to cause excitation of electron, and these electrons can easily jump from valence band to conduction band, creating electron hole pair. And this third process, in which light radiation is used to create electron hole pairs, is basically used in solid state array detectors. And finally, the digital signal. And the digital signal that is obtained is further processed through filtering and baseline correction, because there may be certain background radiations, or there may be certain noise. So those noise can be removed by just doing a blank run, as I told you earlier as well, that in order to remove the background radiations and in order to remove the noise in the spectrum, we first of all do a blank run in which the analyte is not present, while all other things except the analyte are present. We carry out that particular run, and then when the experimental run is carried out in which analyte is also present, we subtract the background radiations in this way, and a perfect spectrum is obtained. The final refined data is presented on a computer screen that can be used for the study of the sample, that ultimately helps us to identify the type of sample, its nature, its structure, as well as its concentration. So the data thus obtained can be used for qualitative as well as quantitative analysis for both. Thank you very much. So we have completed the instrumentation of molecular fluorescence spectroscopy. In the next lecture, I'll explain you how these measurements are carried out, how we prepare the sample for fluorescence analysis, and how the spectra is generated, how studies can be carried out, and what are those specific compounds that are being studied by molecular fluorescence spectroscopy. Till then, thank you very much.